Welcome to Module 2, Lecture 3 of the course VLSI Design, Verification and Test. We have been discussing resource constraint scheduling. The general problem of resource constraint scheduling is NP complete, and therefore different strategies for solving this scheduling problem exist. There are optimal solution strategies, heuristic fast solution strategies and stochastic solution strategies. So, before going into other algorithms, we will first try to characterize the problem by designing the ILP based problem formulation for the resource constraint scheduling problem. Now, the ILP based scheduling model starts by defining a set of binary decision variables. Here we have the binary decision variables x, and x equals to xil, where I goes from 0 to n and L goes from 1 to dot dot up to lambda plus 1. So, here index I denotes operations and L denotes time step, and xij, the variable xij will be equal to 1, will be set to 1 only when the ith operation is scheduled to start in time step or C step j. So, xij equals to 1 implies that ith operation starts in C step j, and lambda represents an upper bound on the schedule latency. So, for example, in the operation constraints graph that we have been studying, the ASAP schedule had given us a latency bound of 4, and we can have other latency bounds, and on that latency bound we can perform a similar scheduling. We are saying that an operation will be 1 when that operation is scheduled in a given time step. Now, therefore, if we have the ASAP and the ILP times for the ith operation, say we have the ASAP as soon as possible time to be TIS, and given any latency bound, let us say that the ILP time of the same operation is TIL. So, therefore, in my schedule in the solution, this ith operation can start at any time between TIS and TIL, between the ASAP and ILP time. However, an operation must have a unique start time. The same operation in the same solution cannot have more than one start times, right. So, therefore, to denote this through a constraint in the ILP model, we have an objective function and a set of constraints. Now, to model this as a constraint that an operation can start at a single one and only one time step, we apply the following that is shown here in the left. So, summation L equals to TIS to TIL, XIL equals to 1. So, if XIL is greater than 1, because XIL can only take value 0 or 1, XIL equals to 1 when operation I is scheduled in time step L and XIL equals to 0 otherwise. So, there can be only one value of XIL, which will be 1 between its ASAP and ILP times, and hence summation XIL equals to 1. Now, given this ASAP and ILP times, what will be the start time of that operation? The start time of that operation can easily be denoted as shown on the right of this slide. Ti equals to L equals to TIS to TIL summation L into XIL. So, for example, let us say that I have an operation that has actually started in time step 3. It is possible to schedule it in, say, time step 1, 2 or 3, and in a given solution my ILP has found that I should be scheduled in time step 3. So, xi3, the ith operation xi3 will be equal to 1. So, Ti will have the value 3. So, this therefore correctly models the start time of a given operation. Now, we will take an example and see how this constraint can be applied on the example operation constraints graph that we have been using. So, in the operation constraints graph, we see that for all operations having 0 mobility, it can only have one start time. The 0th operation can only start in time step 1, 1 and 2 can only start in time step 1, this can only start in time step 2, this can only start in time step 3, and the 5th operation can only start in time step 4. We are seeing that x01, which tells me that the 0th operation in time step 1 should be 1. x11 tells me that the first operation in time step 1 should only be 1. For any other time step it should not be 1. The second operation should also be scheduled in time step 1, and hence x21 equals to 1. x32 equals to 1. Why? Because the third operation should only be scheduled in time step 2 and nowhere else. Why is x43 equals to 1? Because the fourth operation similarly should only be scheduled in time step 3. Similarly, x54 equals to 1 and xn5, which is the last operation, should be 1, because the start time of the sync node should be 5th time step, because the schedule should complete in 4. Now we look at operations having mobility 1. Which are the operations? We see here operation 6 and operation 7. So we have to model that operation 6 can be scheduled either in time step 1 or in time step 2, but in any one of them, not in both of them. Similarly, operation 7 can either be scheduled in time step 3 or time step 2, but not in both of them. Hence, what do we have? x61 plus x62 equals to 1. Similarly, x72 plus x73 equals to 1. So, x72, for example, x72 plus x73 equals to 1 tells me that the 7th operation can be scheduled either in time step 2 or in time step 3, but not both. Similarly, for operations having mobility 2, we have this. The 8th operation can be scheduled in time step 1, 2 or 3. So, x81 plus x82 plus x83 equals to 1. Similarly, operation 9 can be scheduled in either the 2nd, 3rd or 4th time step, hence x92 plus x93 plus x94 equals to 1. The 10th operation can be scheduled in the 1st, 2nd or 3rd time step. Similarly, the 11th operation can be scheduled in the 2nd, 3rd or 4th time step. So, after we have modeled the unique start times of each operation, we come to the next constraint. The next constraint is dependency constraint. What does it tell me? That operation, for example here, operation 3 must be scheduled only after both operation 2 and operation 1 have been scheduled. Only after both operation 1 and operation 2 has both been scheduled. Again, for example, operation 7 must be scheduled only after operation 6 have already been scheduled. Right? So, how do we say that? As we said in the previous slide, that this represents the start time of operation J. So, the left one, this indicates the start time of operation I, this represents the start time of operation J. The start time of operation I should be after operation J starts and the whole propagation delay of the jth operation is also crossed. So, therefore, the delay or propagation delay of operation J plus the start time of operation J should be the earliest start time of operation I. This is what it says. So, the start time of operation I should be at least the start time of operation J plus the delay of operation J. When has this to happen? When there is a dependency constraint between operation J and operation I, shown through the edge Vj comma Vi. If there is an edge Vj comma Vi, then this one should be true. Okay. Now, in our example, we don't show all the dependency constraints here, but show only the non-trivial dependency constraints. For example, and what do we mean by non-trivial dependency constraints? Those dependency constraints involving more than one possible start time for at least one operation. So, what did we say, that all operations in the critical path, operations 1, 2, 3, 4, 5, all of them have only one start time, one possible start time. So, there is a trivial constraint will always exist. That means that operation 4 should only complete after operation 3. Now, in our operation constraints graph, another assumption is that all operations have unit delay. So, therefore, dj is always equal to 1. For all operations j, dj is always equal to 1. So, our non-trivial operation constraints become this. For example, as we said, there is a constraint between operation 7 and operation 6. So, how are we representing that? This part, this one is this one here. So, summation L into xil. Here we are saying that the 7th operation I equals to 7 and time steps are 2 and 3, L equals to 2 and 3. So, we know that the 7th operation can start either in the 3rd time step or in the 2nd time step. So, if it starts in the 2nd time step, its time is given by 2 into x7 comma 2. If it starts in the 3rd time step, its time is given by 3 into x7 comma 3, because only one of x7 comma 2 or x7 comma 3 can be 1. So, the value of this expression 2x7 2 plus 3x7 3 can either be 2 or 3, right. Now, continuing, the second part here, x61 plus 2x62, this part is therefore denoted this one. So, it says that the 6th operation can either start in the 1st time step or in the 2nd time step. And how do we denote its times? So, it can be either x61 1 into x61 or 2 into x62. So, the start time is denoted by this expression. Now, what we are saying, that the difference of the start times, which is given by 2x72 plus 3x73 minus x61 plus 2x62, this is the difference of the start times of 7 and 6. This has to be separated, these start times has to be separated by at least 1, because all operations are unit time operations. This has to be separated by at least 1, and therefore, we get this whole corresponding expression here. This inequality represents this constraint. So, similarly, we get other constraints as what? As there is a constraint between 9 and 8. The start time of operation 9 is represented by what? 2 into x92 plus 3 into x93 plus 4 into 9x4. The start time of operation 8 is represented as x81 plus 2 into x82 plus 3 into x83. Now, again, the difference between the start times of operation 9 and operation 8 has to be at least 1 and is therefore represented by this constraint. Hence, progressing in this way, we get the constraint between operation 11 and operation 10 as because operation 10 can be scheduled in either the 2nd, 3rd or 4th time steps. So, its start time is represented by 2x11 2 plus 3x11 3 plus 4x11 4, and the start time of operation 10 is represented by x10 1 plus 2x10 2 plus 3x10 3, and these two start times must be the difference of these two start times must be at least 1 and is represented by the third inequality shown here. Similarly, another non-trivial constraint is between operation 5 and operation 7. Another non-trivial constraint is between the sync node operation n and operation 11, and finally we also have the dependency constraint between the sync node nth operation and operation number 9. So, these are all the non-trivial constraints that are possible in our example operation constraints graph. Now, we have the final and the third type of constraints, which are the resource constraints. So, at each time point resource bounds must be met. Why is this important? As we said, this is resource constraint scheduling and we only have a limited number of resources of each type. Now, to do that, we first have a small definition here. An operation Vi is executing in C step L. When is it executing in a certain C step or a current time step L? When the operation has started at most Di time steps earlier. So, if Di is the delay or propagation delay of the ith operation, and if this ith operation is executing at the current time step, it must have started at most Di time steps earlier. It cannot start earlier than this. So, we represent that in this term. So, m equals to L minus Di plus 1 to L. So, this represents the time it goes back at most Di time steps from the current time step and finds out whether it has whether the operation has started at any time between the Dith previous time step and the current time step. If it has started this at most this time steps earlier, then it is also currently executing. So, given this we obtain the constraint as given below here. So, for each type of resource that we have, so for each type of resource K, we said that K denotes the types of resources and AK denotes the number of resources of type K. So, at each time step not more than AK operations that needs to be scheduled on resources of type K can be concurrently scheduled. What do we represent as the constraint here? Speaking again, if we have a resource of type K and we have AK resources of that type, we cannot schedule more than AK operations that needs to be scheduled on this resource type at any given time step, right? And so, herein this the term that we defined here becomes important, because this term here tells me that the ith operation is running in the current time step or not. If this summation m equals to L minus Di plus 1 to L x I m is equals to 1, that means that in the current time step L, my operation, this operation, the ith operation is still executing on some resource of type K. Now, then what does this summation tells me? That for each type of resource, the total number of nodes or operations that can be concurrently operating at this current time step is limited by at most AK. This is what this resource constraint tells me. Again, as we proceed to we now proceed to the example as we have been doing. So, let us assume that we have two ALUs and again two multipliers, two ALUs and multipliers. So, the ALUs are used for the operations plus, minus and comparison, and the multiplier is used for the star or multiplication operation. Now, what we will do? We will now therefore, as we have said, for each resource type at each time step the resource constraint has to be satisfied. So, hence for the first time step for the multiplication operation, what do we have? We say that x11, what are all the possibilities? The first operation has a possibility of being scheduled in time step 1. The second operation also has a possibility of being scheduled in time step 1. The sixth operation has a possibility of being scheduled in time step 1, and the eighth operation also has a possibility of being scheduled in time step 1. There are no other multiplication operations that can possibly be scheduled in time step 1. So, among these 4 possible operations, the constraint tells me that at most 2 of them can be scheduled in time step 1. Why? Because we have a resource constraint of 2 multipliers. At time step 2 similarly, x32, that means the third operation can be scheduled in time step 2, the sixth operation can be scheduled in time step 2, it can also be scheduled in time step 1, but can possibly be scheduled in time step 2 as well. Similarly, the seventh operation can be scheduled in time step 2, the eighth operation can also be scheduled in time step 2, and these are all multiplication operations. It may be noted that operation 1 and operation 2 having mobility 0 cannot be scheduled on time step 2, and hence we have the resource constraint for time step 2 as follows: x32 plus x62 plus x72 plus x82 less than equals to 2. In time step 3, what do we have? x73 plus x83 less than equals to 2, because in time step 3 what can be scheduled? Either the eighth operation, which has a mobility of 2, can be scheduled in time step 3, or the seventh operation, which can be scheduled in either time steps 2 and 3, can be actually scheduled in time step 3. So, the resource constraint at time step 3 for operation multiplication becomes x73 plus x83 less than equals to 2. Now, we come to the resource constraint on the addition, subtraction and comparison operations that has to be performed using the ALU, the 2 ALUs that we have. So, what do we have? We have a single operation, the 10th operation, that can possibly be scheduled in time step 1 using the ALU operator, ALU resource, and therefore, we have the constraint as x10(1) less than equals to 2. In time step 2, what do we have? The 10th operation can also be scheduled in time step 2, the 11th operation can be scheduled, possibly scheduled in time step 2, and the 9th operation can be possibly scheduled in time step 2. So, what do we have? We have the constraint as x92 plus x102 plus x112 less than equal to 2. So, although we are assuming here that it is possible to schedule the 10th and the 11th operations together, this possibility will be discarded by the dependency constraints that we have seen in the last slide. So, for the third time step, what do we have? x43 plus x93 plus x103 plus x113 less than equals to 2. And lastly, at the fourth time step, we have x54 plus x94 plus x114 less than equals to 2. These are all the resource constraints that we have for our example. Now, given all these constraints, we can now obtain our final ILP formulation. Now, the formulation will first have an objective. Now, here we have put the objective as to minimize Tn, that is the start time of the sync node or the nth operation. Now, if we minimize the start time or the sync operation, that means we are basically minimizing the length of the schedule, right. So, therefore, the final formulation becomes minimize Tn such that, and Tn can be obviously alternatively represented as summation L equals to Tis to Tns to Tnl L into xnl, the time at which Tn is scheduled, the start time of the nth node. Now, therefore, we can obtain the final formulation as minimize Tn such that all operations have a unique start time, all dependency constraints are satisfied, all resource constraints are satisfied, and the last constraint being that our decision variables xil are binary, right. Just to say that let us say if my objective function would be a bit different. For example, instead of trying to minimize the nth operation, that means the start time of the sync node, if you want to minimize the summation of the start times of all nodes, just arbitrarily speaking, if we had this one, then our whole optimization problem would be a bit different. As we know what will then be the objective function, because we now know how to represent the expressions for the start times of all these nodes. Therefore, our objective function will therefore be an addition over the start times of the of all nodes in my operation constraints graph, and each start time is represented by its corresponding expression. With this, we come to the end of module 2 of lecture 3.